Awesome. So welcome everyone to the live stream. Finally, we are on. This is rather awkward and embarrassing, but it is what it is. So welcome to the Discrete Math live stream. And today we're gonna look at basically two topics, which is logic and proofs. So the sequence of events today is that I'm going to cover two questions from logic, followed, three questions from logic, and followed by Q&A pertaining logic. This includes propositional and predicate logic, followed by the question 3 in our notes, which is one on proofs. If you are here not from the module in the college, but you're here because you came from other parts of the YouTube channel, welcome. We're gonna do a bunch of questions followed by some Q&A pertaining logic, and then we'll do one question and then some questions pertaining proofs. Right? I will address all of your burning questions, but let's sort of set the stage with some existing questions. So let's first look at this question, which basically asks us to determine whether or not these two compound expressions are equivalent to one another. And in general, the thought process I have before I even solve the question is to note that implications generally don't behave as well as other kinds of logical operations. And what that means is that, well, in particular, just to recap for everyone's benefit, if we were to draw the truth values for P and Q, if we were to draw the truth table for P implies Q, we will get this irritating sort of situation called vacuously true. And that could raise some troubles, right? For everyone who is here, feel free to say hi in the chat. This could create some problems for us. So I remembered that one of my students actually came up with a brilliant proof that really helps to make life much easier and helps to answer some other questions as well. So what my student did is take advantage of the fact that P implies Q, the implication can be written as a disjunction. If you want a quick explanation as to why this is the case, you can go check out my propositional logic live stream somewhere else on the channel. And so his idea was to convert each of these expressions using this writing the implication as a disjunction. So we can write this as the negation of P, or Q implies R. This is by implication. And we can do this a second time because because Q implies R itself is an implication, which means you can write this as negation of Q or R. So this is also by implication. Okay. Now, the second part of this simplification happens over here. So he does the same thing, and he is writing this as the negation of the first guy or the second guy. Right. However, in the expression on the left, we are negating an implication, and we can actually use De Morgan's laws to show that the negation of P implies Q is precisely flipping all of these terms here, which means we can write this as P and negation of Q or R. We can write this as implication. Oops. And we can write this as De Morgan's laws. Now, the thing over here is that once you have these expressions, it is not too hard to come up with values of P, Q, and R so that these compound expressions, when you substitute the propositional variables, evaluate to different truth values. So the idea is that if we choose P, Q, and R judiciously, we will be able to obtain a disagreement in the truth values. In fact, the choice that we are going to work with now is going to be false and false for P and R. You might be wondering why we're doing that. Well, for the first compound expression, this will evaluate to the negation of false disjunction with anything. The reason why this is useful for us is because the negation of false is true, disjunction with anything, which evaluates very simply to true. On the other hand, if we were to plug in p equals to false and r equals to false, we're going to get false conjunction with something, or false. And we know that when you take false conjunction with anything, the result will always be false. And when you take false disjunction with false, you will get false. The point here is that by plugging in these two values, you will obtain different truth values. And Q, you can actually pick anything you want for Q. No one really cares what Q is. So you could pick PQ to be true, you could pick Q to be false, and in both situations, you will still obtain this disagreement in the truth values, and therefore you can conclude that they are not equivalent. These two compound expressions are not equivalent to each other. Okay? So that's the main bit here. Now, here's the fun part for the next part, right? And after this, we'll do one more question and we'll go into a Q&A. So another question that we are interested in is whether these propositions, or rather these compound expressions, are these compound expressions equivalent to one another? And it turns out that after you experiment a little bit with some of the truth values, you probably would suspect that these two things are indeed equivalent to one another. But how will we go about proving it? Now, one way to prove it is to run through logical identities. That might take some effort. So I'm actually going to revert to the good old truth table approach. Okay. Now this could also take some time, but it's not too bad. It only requires, it doesn't take too much time. Okay. So let me just write down the quantities we're interested in. Okay. Oops. Okay, so we are interested in these quantities. These are all the different possible truth values for P, Q, and R. And I'm just gonna plug in the true values here because I'm really lazy, right? I'm not gonna bother with the falses. So this is true precisely when these truth values agree with each other. So this is trues. This will be a true. This is true. This is a true. These two don't agree with one another, so I'm going to leave that blank over here. These two don't agree with one another, I'm going to leave that blank here as well. These guys are both falses, so they do agree with one another, and therefore these guys are going to be true as well. So we can run through this line of reasoning, and we will obtain the following truth values. Right, and for Q implied for the bicondition between Q and R, we're going to get this one. And finally for P and I need to compare these two truth values together. So this will evaluate to true, this will evaluate to true, these guys are going to evaluate to true as well, and I don't think anything else does. So this is going to be true, 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 and true. And indeed, we do see that this entire column right here and right here, they do agree with one another in terms of the truth values. So if you're wondering, here's a little hack to do a truth table, right? You just work on the true values and then you fill the rest in with falses. You're going to see that in however you do it, the two columns agree. Therefore, they are equivalent. These are equivalent to one another. Okay. Now, one last question and then we'll go into a Q&A in terms of logic. Just one last question. And afterwards, feel free to release your questions before we go into proofs. So the last question is to establish that this is called a proof by contradiction. The claim is that this thing is a tautology. The claim is that this compound expression is equivalent to a tautology. So how do we go about doing that? Now, the key insight in this question is just like the first bit, the first trick that one of my students suggested, which is the fact that when you take P implies Q, this is equivalent to the negation of P or Q. Likewise, if you take the negation of that, by De Morgan's laws, you can flip everything accordingly. So what that tells us is that we can try to apply this little trick throughout this argument. So the first thing we see here is an implication. So let's use the implication law. Followed by the negation of an implication. So the negation of an implication tells us that we are getting P, now it's the first guy, and the negation of the second guy. This is by De Morgan's laws. Well, the negation of a contradiction is going to be a tautology. Whoops, should do that. The negation of a contradiction is a tautology. And when you conjunction any sort of compound expression with a tautology, you're gonna get the expression itself. Now, I do not know what, I think this is called top-bottom. I do not really know what the name is. Honestly, to this day, I still do not know what it is. All I know is that the negation of a contradiction makes sense. It does give you a tautology. And when you take the negation of, when you take a proposition conjunction with tautology, you get the same thing. We call this identity. And of course, finally, we'll get that if you take the negation of a proposition disjunction with the original proposition itself, well, a proposition is true or false, so in either way, at least one of these two things must happen. We will get, in fact, a tautology. Okay, so there's a very quick proof for the fact that the proof by contradiction is a valid proof technique, and you can use it to derive many interesting ideas. So, without further ado, let the questioning begin. Come on, feel free to raise your questions in the chat room. We'll probably continue with the proof segment in about, say, about 11:15, about there, and then we'll do a quick one before we answer the questions for proofs. All right, so you guys got the questions? Take it away. Any tips for the quiz? You probably want to try some of the further exercises. You want to work on those calculation type questions because those calculation questions do actually carry quite a few weight. So I think, for example, maybe we can I can look at one of these questions in the predicate logic segment. Just give me a moment. Let me just highlight one of them. I've covered this in a different stream, but feel free to work it through. So for example, this one over here, suppose we have D being the set of 1, 3, 5, 7, 9, 11, and 13. And you want to ask whether or not, say, this proposition, where E is the set that contains this, right? Is this true or false? I'm not going to solve the entire question. I did it somewhere else. But let's just say, is this true or false? That's the question, right? Is it true or false? Well, from the onset, it may not be so obvious, right? But what is this question sort of telling us? Well, for any item in here, you can find an item in here such that such that the item in here is smaller than the item in here. Well, it sort of makes sense because if you think about it, if x is okay, so for any x in D, fix x in D. All right, we've got another question pertaining implications and conjunctions. We're gonna look at that in a moment. So if we fix x in D, then either x is either smaller than or equals to 7, or x is bigger than 7, and then you can sort of argue your way through to show that in both cases you do get a true outcome. Right? You essentially, for the numbers above 7, you can choose y equals to 6, and then for the numbers below 7, you can choose y being equals to x minus 1, which will always belong in E. Right? So that's just an example. In fact, you can go one step further. You can even say this. You can just choose y equals to 0, right? Then y is always less than x. Y equals to 0 is always less than x. So you get true. So you want to try these kind of questions where you are required to look at a set and determine whether it's true or false by identifying. These are more concrete. Alright, so here's the question in terms of implications. Really important bit over here. So the big question, what is the difference between P implies Q and P and Q? Right? Okay, so the main difference here is the fact that in the first case, we do not really care whether P is false or not. We do not care. So let's just say, for example, if Joel is taking CS1231, he will wreck the bell curve. I think that's a debatably true proposition right there. Versus Joel is taking CS1231 and he will wreck the bell curve. Okay, so what's the difference between these two? Well, in the first scenario, if Joel is not taking CS1231, then no one cares about what happens. We call the statement is vigorously true. But in the second case, if Joel is not taking CS1231, I will actually evaluate this whole expression to false. Right? If Joel is taking CS1231, it's false. So that's the main difference between implications and conjunctions. Basically, you want to ask whether or not if the condition in the front, right, if that's false, do you reject the whole statement or do you keep the statement? If you keep it, use implication because no one cares. But if it does cause the entire statement to be false, then you want to use conjunctions instead. So this is pertaining implications, this is pertaining conjunctions. Now, is it necessary to state the name of the operation for each step, or is it enough to just state the logic in English? I'm not too sure what the question refers to, but I'm not sure. It depends on what kind of proof you're working on, right? So in general, the rule of thumb is you want to justify your steps, right? Whatever working you're doing, you want to justify it sufficiently so that you are not only correct, but you are correctly correct, if that sort of makes sense. Yep, so that's the main thing. But feel free to clarify the question, and I'll be willing to answer that as well. Yep. I would actually both are equivalent, or rather both are two ways of saying the same thing. Let something be versus set something be. So what I like to, or rather yeah, okay. Oh, for the first question, yeah, of course you could choose different y's for different x's. That's fine. Choosing y equals 0 is the laziest approach. Now for this bit, oh yeah, this is recorded. This is it'll be kept on YouTube. Now back to the question. When you use let something be, same thing. So for example, if I need to prove for any x in D, there exists y in E such that pxy, for example, for instance, you could say let x be an element in D. You can start it this way. You can say set x starting in D, and you can say fix x in D. Either are basically two ways of saying the same thing. Yeah. So honestly, sometimes if you do it carefully, set might be linked to the to the there exists bit. So like for example, choose y equals to whatever, which belongs to E, blah blah blah, right? I would use some people would use set y equals to this in E, blah blah blah. I think this is still acceptable, right? But you have to be clear on what you're doing, right? It's not always these two sets here sort of have a different meaning, right? So it depends on context. My favorite option is to just fix and then choose, right? So choose y equals to something belongs to E. Yeah. The live stream will remain on YouTube. It's all good, all well and good. Can I state? Oh, I think you can. I would think it's possible. But I mean, if you can bring the materials into the notes, if you can bring the notes into the examination, then feel free to just use the name. I mean, it's no harm being able to know that that's the terminology. I will say this though, when I solve problems, I tend to avoid doing these things first. I'll focus on just trying to calculate this, and then later on, when I'm done and when time permits, I will go in to fill in the names of the properties. Yeah. All right. Final calls for any logic related questions. If you guys are good, we can actually head on to the proof section already. But I'm gonna just let you guys ask your logic questions first. Of course, we can do the proof first, and then the rest of the night. The night is young, right? You can basically ask any question you wish. Okay, so any people who want to any desperate questions to unveil first. Okay, so this is a proof by cases. So that's the claim. The claim is that this thing. By the way, I am going to release a discrete math in a nutshell video. I've already prepared it. It's scheduled for YouTube. It's going to be released soon. I will let you guys in when that happens. I guess you can subscribe if you want to be the first to know when it drops. Alright, so the claim is that, this thing is a tautology. This thing implies R is a tautology. So what's the logic here? Okay, so the intuition here is that if you have P disjunction Q, you can and you know that P implies R, and you know that Q implies R. What's the conclusion that you can make? You know at least one of these things hold, and you know that no matter whether P holds or Q holds, both will cause R to happen if P and Q are true. This allows you to conclude that R is legitimate as well, right? Thanks, appreciate it. Now, so this is the claim, and we can actually go ahead to prove the claim. I am thinking of, well, I might try to prove it using truth tables, but this is going to be a really tedious calculation. Well, let's give it a shot, right? So here's the assumption. We notice that as long as one of these guys are false, the entire implication is going to be vacuously true, right? So we can first maybe focus on these guys being true. Okay. Okay, so yes, the sleight of hand trick. We're gonna look at that in just a moment. Okay, we're gonna do that in just a moment. Okay, I part of me really do not want to prove this result. But we can do it. Let's just do it. Let's just do it. You know, let's not be cowards, right? Okay, but I'm going to go a little bit more quickly with these with these calculations here. Okay, so P Q R P or Q. Okay, P implies R, Q implies R. Okay, so let's just do it really quickly. I'm not gonna fill in the falses. I'm just gonna put the truths. Okay. Right, and then this is the last bit of it. So the disjunction of P and Q will be these guys. The P implies R is going to look like this. Q implies R looks a bit like this. And the conjunction of all three of them, right? The conjunction is going to be true, right? And when these guys are true, R is true, and we're good to go. You can fill in the details if you want. The rest is on the channel. Now we're gonna look at 3.3 in just a moment. Oh, by the way, the intuition for the proof by cases is this bit over here. This is the real intuition over here. Okay. But the proof is using truth tables. I did this in the other video. Now 1.10. I did that in the other video as well. Alright. Okay. More than willing to. Now this is more for proofs than logic, but what thought process do you recommend if you feel stuck on a problem? If you come across something and don't know what steps to take to get to the answer. So the rule of thumb, generally speaking, most problems in an elementary discrete math course are going to be relatively simple, in the sense that if you unpack the definitions properly, the answer tends to pop out relatively quickly. Okay, so we'll definitely look at a little bit of that in the next when we do 3.3 in just a moment. But roughly speaking, that's the thought the thought process. I always first unpack the definitions, and then I always ask myself, what have I not used in the question? Most questions at the year one undergraduate level tend to be solvable, okay, with a bunch of what we call definition chasing. Just unpack the definitions and ask yourself, what have you not used in the question? We'll take a look at that in a moment. Okay, 1.10. Okay, so 1.10, let's do 1.10 really quickly. Okay, so what's 1.10? Here is we're given, by the way, from a previous question, that P, the biconditional is a tautology precisely when P and Q are equivalent. So the claim here is that P equivalent to Q implies that the negation of P is equivalent to the negation of Q. Right? So so here's the proof. Here's a really quick proof of this claim. So we're given P equivalent Q. Isn't rule 5 true as well? Did I miss rule 5? Yeah, I think I missed rule 5. Yeah, thanks for that. Yeah, and I think rule 7 as well. Yeah, this should work. Oh no, rule 7 is oh yeah, okay, sorry, just rule 5, yeah. Yeah, rule 5. Okay, so where are we? P equivalent to Q, right? Well, this tells us that P, left right arrow, Q is equivalent to a tautology, which means that P and Q always share the same truth values. But that also means that if you negate both sides, you're going to get the same truth values as well. Which means that negation of P, this thing is a tautology, which means that negation of P is equivalent to negation of Q. It's sort of a semi-roundabout way of thinking. I do think that you could actually get by with this argument. I do think this is you can get by with this argument. Yeah, it does make sense. Yeah. This is true. Yeah, this works. Okay, so there's that. So that's 1.10. That's a relatively short exercise there. Okay. Using the given claim over here. We were given this in a previous question. Okay, now let's go ahead to work on a proof question, which will help you guys quite a bit with thinking about proofs. So here's the claim. Okay, so let's just first write down what objects we're given. We're given that Pxy is a predicate, aka a sentence that becomes true or false when you substitute values, on the set A. We're gonna claim this bit over here. Okay, so we have two expressions which are quantified. And you're gonna notice that the difference here is the fact that one of them is a single direction and the second one is two directions. For 1.10, can you use proof by cases? Sure, yeah, that works. Yeah, if P is Q, then so on and so forth. It's essentially the same argument, so it works. Right, so for this bit over here, the fact that, generally, as we've discussed just now, single arrows and double arrows tend to not have very nice behaviors. But it turns out that the claim is that, or rather we're given these ideas, the claim is that these two guys are equivalent. Right? That's the claim. And we want to prove this claim. So, we're going to prove this claim, and the way we're going to prove this claim is to invoke a two-directional proof. So what's a two-directional proof? Well, we first need to prove that the left side implies the right side, and we also need to prove that the right side implies the left side. Right? Some of you might be wondering, why not take false imply false? Why not try to show false implies false? You could try that out, but essentially you're proving the contrapositive of this step. Right? Feel free to ask me more questions on why that's the case in just a moment. For now, we're gonna just use this proof strategy. Now, what is this proof strategy? The proof strategy is to first suppose that 1 is true, and the goal is to prove that 2 is true. And that's for the forward direction. For the reverse direction, we're gonna follow the same approach. Suppose that 2 is true, and the goal is to prove that 1 is true. So this also helps sort of address a little bit of the question pertaining proofs and logic. This is what I tend to do first. At this point in time, I actually do not even know what part 1 and part 2 refer to. Right? I'm just writing out the goal, which is to prove that we get an equivalence between these two sentences, propositions. So now I need to go back to ask the question, what on earth is 1 and 2, right? Now, to suppose 1, it means I can suppose that this statement, for any xy in A, we get this implication. This whole thing is true, right? That's what it means to suppose 1. We suppose that this implication is true. We'll come back to this supposition in just a moment. Okay, but let me add some space because we might need some space for later. So we need to suppose this is true. And what's the goal? The goal is to prove 2. Well, what is 2? Well, 2 refers to this universal statement. So what do we need to do? We need to show that no matter which elements x and y you pick, this proposition works. So to make things a little bit clearer, I'm going to fix R and S inside A. That is choosing the elements inside the set A. And the goal is to prove that this implication holds. That's the goal. The goal is to prove this implication holds. Now, with this goal in mind, what exactly is our goal? Well, our goal is to prove that our PRS and PSR, have the same truth values. But that simply means we need to basically break this down one more time. What's our sub goal? Our sub goal is to prove that if we suppose PRS, or rather our subclaim, this is a subclaim, we need to prove that PSR works. This helps us establish this direction. And we have another subclaim, which is to suppose PSR is true, and we need to get to PRS being true. So those are the sort of the two goals of this, right? This first subclaim helps us prove this direction, and this subclaim helps us prove the reverse direction. Right? We can prove the two directions in this way. So now we're gonna work on each of these subclaims. So here's the first subclaim. Suppose PRS, our goal is to get to PSR. Now what? Right? We're stuck. Well, this is where I need to ask myself the question, what have I not used in the question, right? So what have I not used in the question? I've actually not used the fact that we have this proposition here. Now, some of you might have noticed that there's actually a faster way to prove this result, but I'm sort of breaking down a problem if it's the first time I've ever seen it, right? I'm just going to break it down to its rudimentary goals and ask myself, what am I trying to achieve, right? The first idea is to, if the goal is to show that 1 implies 2, we can unpack the meaning of 1 and try to interpret 2 as follows, as this subclaim, whatever. And then you can break this goal further down into 2 other goals. So you sort of break down the big problem into smaller chunks, and you sort of solve the smaller chunks to get to the bigger result. So suppose PRS is true, we do know that R and S belongs to A, which means we can substitute X equals to R and Y equals to S. This is called universal instantiation. I just learned that from one of my students last week. And we get the implication being true as well. Now, when I don't write anything here, I mean this true, okay? So we have the starting point, and we have a bridge that goes from the start to the end. Can we conclude that the end is true? Well, the answer is yes, because we have this proof technique called modus ponens. Right? We have this proof technique called modus ponens. And in fact, this is precisely the goal that we have here. Now, I don't think that really gave a lot of people a lot of problems. The second one was what makes the question a little bit more tricky, right? So this is where I pulled a sleight of hand. I substituted x equals to s and r equals to, y equals to r into the given proposition. Now, since s and r are items in A, we can substitute x equals to s and y equals to r to obtain this implication. But once again, by modus ponens, we get PRS, which is precisely the goal that we were looking for. Right? So in fact, we have accomplished both goals, which means we have proven this goal. What have we therefore accomplished? We have actually proven that if we fixed R and S in A, we obtain this result. But what does that mean? It means that we have met this goal. And that was the first part of the proof. It's in one direction. Now, some of you would actually notice that we could actually condense this argument, and I'm actually going to present the condensed argument in the reverse direction. So stay tuned for that. Now, we need to suppose that 2 is true. Well, what does it mean for 2 to be true? It means that for any x and y in A, Pxy is equivalent. Well, there's the biconditional. We have this whole expression being true. Well, what's the goal? The goal is to show 1. What is 1? If we reinterpret 1, it means if we were to fix R and S in A, we want to show that PRS implies PSR. And at this moment, you could break down this problem once again and prove it just like we did just now. However, I'm going to cheat a little bit because there is a little hack that we can use even for the previous part. And this is the hack, right? Well, since R and S are in A, we can substitute x equals to R and y equals to S, once again by universal instantiation. We can plug in x equals to R and y equals to S and get this proposition for free. However, this means that we get the two directions as both being true. And this is from a tutorial exercise. But if both parts are true, then each one of them is true. But this is precisely the goal that we had in mind. Okay, so this is sort of the sleight of hand approach pertaining this question, or at least the previous part of the question. Right, so that's roughly speaking how you go about thinking about a proof. You really break it down to the sub-goals according to what the question says. Right? Just within what the question requires, we can break it down and answer the question accordingly. That is how most proofs at the undergraduate discrete math level are. They work. Thankfully, you guys are not dealing with epsilon delta proofs. I do have a few videos on that. I have a video where I explain epsilon delta proofs, and I have a video where I spent 7 hours solving 100 epsilon delta proofs. Knock yourselves out if you're doing mathematical analysis. My research was in math analysis and probability, so that was somewhat interesting. So all's well and good. That are basically the two questions or the few questions that is now online for those who are interested. Feel free to raise questions pertaining proofs. We do any questions or whatnot, feel free to raise them in the comments. And then the night is young, right? So take it away, guys. Or enjoy the music, or study if you wish. Just chill out. When is it best to do a proof by contradiction? Alright, that's a really good question. It's an easy way to tell it worked well for a certain problem. So, proof by contradiction essentially means you want or rather, the way we use proof by contradiction is to give us more tools to solve the problem. Okay, so what do I mean? So there's a really classic question. I think you've probably seen this many times in various sources one way or another. If not, welcome. Here's a claim. The number, the square of 2 is irrational. And how do we prove it? Well, what does it mean for a number to be irrational? It means that it's not rational. How do you prove a number is not rational? Well, it's really hard, right? Like, what does it mean even to be not rational? What are properties do we have about numbers that are not rational? And it turns out there are many ill-behaved properties about numbers that are not rational. So the reason why that is a problem is because if you try to prove it directly, and there are technically ways to do it, involving some interesting theories about continued fractions and whatnot, but when you're first starting out with proofs, there's no real useful way to tackle this proof because you don't have any tools pertaining irrational numbers. However, if we suppose that root 2 is rational, now here is where the fun begins, because now we have tons and tons of proofs involving, or not proofs, tons of results and properties involving rational numbers. Well, we know that if root 2 is rational, then root 2 can be written as m over n for some positive integers with no common factors, right? Because you can always reduce a fraction down to its core two integers. You can square this number. And obtain 2n squared being equal to m squared, right? This tells us that m squared is even, and I'll let you try this out as an exercise to prove that m is even. Hint, you might need another proof by contradiction, right? Or contrapositive, whichever you want. Right? Because you might be able to work more with odd numbers than even numbers. Okay, so by this exercise, we can say that m is even, right? Which means that m equals to 2k for some non-negative integer k. This means that we can rewrite this as this problem, which tells us that n squared equals to 2k squared, which similarly tells us that n is even. So what have we shown? We have shown that, well, if m is even, by the way, that means that 2 is a factor of m. And if n is even, then 2 is a factor of n, which means that m and n have a common factor 2. Now, what does that mean? We have shown that if root 2 is rational, then on the one hand, root 2 can be written as m and n, where m and n have no common factors. On the other hand, we've also shown that m and n have a common factor. How can these two ideas be true at the same time? They can't. You can't have no common factors and common factors at the same time. This is what we call a contradiction. But what did we contradict? We contradicted the claim that root 2 is rational. So if root 2 is rational leads to a contradiction, then we can conclude that root 2 cannot be rational. But that tells us simply that root 2 is irrational. So the point of using a proof by contradiction is the fact that it gives you more tools to work with. You do not know much about irrational numbers, but you have tons and tons and tons of information about rational numbers. So that's the use of a proof by contradiction. Okay, so that's a quick explanation. Could you clarify, please, when can we use modus ponens to prove? Well, essentially, whenever you have an equation of this form, or you have these two statements, P P implies Q, you can therefore conclude Q. Right, so that's essentially what it means. So in other words, if Joel is taking CS1231, he's going to destroy the bell curve. Joel is taking CS1231, therefore Joel is going to destroy the bell curve. So that's essentially the modus-ponens argument. Is this the most simplest way to prove whether a number is irrational? At least based on the tools that we currently have. Feel free to find another proof involving showing the root 2 is irrational without using contradiction. Feel free to go and source it out. I think I can't really think of one at the moment, but this is really the classic introduction to the idea of proof by contradiction. Yeah. Most numbers are not easy to prove that are irrational. Yeah. It's quite difficult. You can try to prove that E and pi are irrational. Those proofs are pretty intense. Yeah. The one that E is irrational is easier than the one that pi is irrational. So that's that. How's the revisions coming along, everyone? I know there's lots of terminology, but my best advice is to sort of familiarize with the tutorial content, and to sort of have a clear perspective on how to approach, or rather a clear perspective on the concepts in discrete math so far. Yeah, go and check out the other live streams if you wish. It's somewhat instructive. How do we go from m equals to 2k from this guy, okay, to this one? Well, we're still given this equation, right? 2n squared equals to m, so we just plugged in m equals to 2k into this thing, right? So then you get that. Yeah. And then this is by algebra. I think you guys can do algebra. I'm quite sure no one here is gonna ask any questions about induction and strong induction, you know, because it's not tested. But yeah, there's that. When writing proofs, as long as my argument is logically sound and I get the desired answer result where I get a full credit, will I be penalized for skipping steps or improper presentation? I think improper presentation might cause you to fail to communicate that your argument is logically sound. So you're right, as long as the argument is logically sound and it's correct, you will get the credit. But if you are presenting in a way that makes the marker relatively confused and not knowing what you're doing, that might run into problems. I have this video, which I'm gonna just put it into the link. It's by this mathematician called Norman Wahlberger. He made a really great video pertaining proof writing. Essentially, how do you write math at the college level? I'm gonna just shamelessly plug his video into the chat over here. So really good stuff. Thoroughly recommend it. There was once I actually did a question in math analysis, right? One of my questions, and there's this really nasty claim and question and all of that, and then we had a claim that if P then Q, and of course P and Q are really specific propositions here. Proof, we're gonna suppose that I think it's supposed if x is a real number or something like that. So I just did suppose x equals to 0, and I managed to get Q, and then suppose x is non-zero, and I actually got stuck. And what I did here is I said we aim to show Q, which means something and something and something. I still remember I got 4 out of 5 marks for this question. Yeah, so do present. If you can't prove the whole question, prove a small special case. That might get you some credit. Can you explain how we know in line 1 of the proof that m and n have no common factors? Is that the definition of rational number? Well, it is sort of a consequence of a rational number of the rational numbers. So whenever you have a positive rational number, you can always find 2 numbers with no common factors, sort of, because you can keep reducing them. So sort of like this, right? For example, if you have 8 over 6, or let's just go a bit bigger, 16 over 12, you can sort of reduce this once to get 8 over 6. We can reduce this another time to get 4 over 3. So it's more of a consequence of the rational numbers. There is a proof for it, but yeah, I think we can use this information for without any proof, as far as discrete math is concerned. Yeah, the proof of this is a little bit more in either a possibly in a number theory course or even in a math analysis course. They might make you do this as well. But usually it's you can use this without proof lah. Yeah. Can you show us some examples of when we use contradiction versus contrapositive? Okay, so here's one. Remember this one over here, right? This one here. We can actually prove this in 2 ways. We can either prove this using contradiction or contrapositive. So just for everyone's benefit, I'm gonna very quickly prove that this claim. Right? Let's do this claim and let's prove it in 2 different ways. I think there was a mathematician who once said that it's more important to be able to have many ways to prove one result, because then rather than being able to prove many results. So here's the claim. M squared is even implies that m is even. So let's prove this claim. Now we can go with this in 2 ways. The first way is through the contrapositive, and the second way is through contradiction. So let's go ahead. Let's do this using a contrapositive. And what do we want to show? So is equivalent. This statement by contrapositivity is equivalent to saying that if m is not even, which means m is odd, we obtain that m squared is odd. How do we go about this kind of goal? We will suppose m is odd and we do not make any other supposition. Now this is key because later you're going to see it's going to be slightly different for contradiction. Contradiction gives you more weapons, but you pay a price for that. What's the goal? The goal is to get m squared being odd. Okay, so let's try to work that out. Well, if m is odd, then m equals to 2k plus 1 for some integer k. But that simply tells us that m squared equals to 2k plus 1 squared. Now you guys can do algebra. I'm going to let you guys work out the algebra. And you're going to get 2 times k squared, or rather 2 times 2k squared plus 2k plus 1. And if you look carefully, since k is an integer, this bit here is an integer, this bit here is an integer, and this whole thing here is an integer. So you have a number of the form 2, let's call this L plus 1, where L being defined by 2k squared plus 2k belongs to the integers. This tells us, by definition, that m squared is odd. And we're done. Right? And we're done. That's a proof by contrapositive. Now let's go ahead to prove this by contradiction. And you're going to see that it can be, sometimes contradiction may come across as more challenging. And there's a reason why. So let's repeat the claim, but now let's prove it via contradiction. But contradiction is overall much more powerful because you have more weapons. So here's the idea. Well, we are going to claim this thing, so we need to suppose the hypothesis. We claim that this is the conclusion that we want to achieve. Contradiction says if this conclusion is false, we will run into problems. Does that make sense? So we're going to suppose for contradiction that m is not even, aka m is odd. Now, compare this starting line with the starting line of a contrapositive. The starting line of a contrapositive says, suppose m is odd. You have one weapon to work with. However, the starting line for this proof, you have two weapons to work with. You have a supposition that m squared is even, and you have a supposition that m is odd. So you have more weapons to work with. What's the goal? The goal is to run into a brick wall, aka find a contradiction. Find a contradiction. What contradiction are we supposed to find? This is the price we pay for having a proof by contradiction. A priori, there's actually no telling what is this contradiction. We're just gonna work things out and somehow pray and hope that we run into a brick wall, which gets us the conclusion that we're looking for. That's the difference. Hopefully you can see that. Even for the root 2 being irrational proof, we actually had no idea. If we look at the proof for the root 2 being irrational, we actually had no idea what the contradiction was. We had to slowly work things out and hopefully run into a brick wall, and it turns out that we did. Okay, so let's do this properly. So what do we have here? Well, we know that m is odd, so we can try to write m equals to 2k plus 1 for some k in integers. You're going to notice that the argument is going to be somewhat similar, but the conclusion, or rather the way we derive the conclusion, is different. So what I mean is this. M squared can still be shown to be equal to 2l plus 1, where l is something, is an integer. This tells us that m squared is odd, which means that m squared is not even. Now, what does that mean? It means that we have a situation where if we suppose that m squared is even and m is odd, we obtain that m squared is not even. That's a contradiction. Or rather, more like this. What do we contradict? We suppose that m is odd, and then we obtain that m squared is not even. But this contradicts the hypothesis that m squared is even. So this is the contradiction. Right? That is the contradiction. The contradiction itself tells us that this is not true. Right? That's what the contradiction tells us. So therefore we can conclude that m is not odd, which means that m is even. Yes, the proof by contradiction always starts with the negation of the statement. It always starts with the negation of the statement. Well, if we were to do that, okay, so actually let's work with that. So this is one way to present a proof by contradiction. To be more precise, and I agree with Deborah, I hope I got your name correct. I don't think my argument here is that sound. Okay, so let me do it more properly. Okay, of course here we are saying for any integer m, this thing, right? So we first need to assume, and I agree with that on this, we need to assume a negation. Or no, we need to suppose for contradiction, the negation. In other words, right, what's the negation of this claim? The negation of this claim is that there exists a natural number m such that m squared is even and m is not even. Now, surprisingly enough, again, the goal is to find the contradiction. If you look carefully, the rest of the argument still holds. We suppose that there exists an m. Now, we're not proving that this is true. We are assuming that this is true. And what does that mean? Do we know what this m is? We have no idea what this m is. How we know it exists? There is an m. We have no idea what it is. Well, so here I'm taking advantage of the fact that m is not even implies that m equals to 2k plus 1 for some k. We have no idea what this k is. All we know is that it exists. And then we derived the contradiction. Now you might be wondering, why did I work with m is not even then m squared is even? For the same reason that we go about with the proof. This gives you more weapons. I can square an integer, get an integer, but taking the square root of an integer is not as certain. I don't have enough tools to make sense of that. So yeah, that's the main idea behind these two proofs. That's the main idea. Yeah. So I agree with that on this. I think we should start with the negation. We should suppose for contradiction that negation is true, and then work from there to obtain all the different results. Yeah. Okay, if there are no questions left, I'm gonna give a final call for questions and then we can call it night. Any last requests for questions from the chat? Okay, if there are no questions left, all the best for your quiz thingy, whatever. Okay, here's one. Which one do you suggest to try? I would usually suggest a... remember, for contrapositive, we are working with implications. Right, so if your problem is not an implication, then you have to try contradiction if you can't do it directly. You can skip. No, please show the algebra. Please show the algebra. I'm just, I'm not doing this in the interest of time. You can check out this video later. It'll be public. Yeah, but I generally suggest if you're working with an implication, you could try a contrapositive, and then if you're not working with an implication and any direct attack does not seem to work, you might benefit from a proof by contradiction. Okay, so I think that's a general rule of thumb. Yeah. Also, if anyone else here is not from CS1231 but is just enjoying this stream, hey, welcome, more than welcome. Yeah. Okay. Any last questions from the chat? Okay. If there are no questions left, all the best, everyone, for your quiz. Yeah, just give your best and enter with a clear frame of mind. I don't know what time is it happening. I'm not invigilating tomorrow, so I'm not invigilating for the quizzes. I was scheduled for it, but then I can't do it because I've got a linear algebra class tomorrow morning. So there's that. Alright, thanks everyone for joining the stream. I will catch you guys when I catch you guys. And all the best. Feel free to text me for any questions. How will you know when your proof sufficiently proves the claim? You check every quantifier and you check that the proposition is indeed true. Okay, so yeah, that's that. And looking forward to